Hello, welcome back. We're now going to discuss a slight generalization of these linearization ideas, and in particular we're going to talk about linearizations around trajectories rather than around equilibrium points. And if you think about it, this is a very useful thing to maybe be able to do. So say, for example, we wanted to send some rocket to Mars or something, I don't know. We might have some nominal trajectory that we want this rocket to follow, and then we might be interested in understanding the deviations of the motion of the rocket about this trajectory. So we've got this path that we want to follow, and but we might get knocked off that path as we go, and we might want to know if we're going to be stable around that trajectory. So will we tend back to that trajectory or go off somewhere else? And so now we're just going to talk about the idea of linearizing around a trajectory. And the main message here is that actually everything we already learned passes through almost uninterrupted. We can linearize about a trajectory in exactly the same way as we linearized about a point. The only difference will be that the A and B matrices start becoming, and also the error terms start becoming time dependent. So they become matrices that depend on time, not just matrices of constants. So what do we mean by a trajectory? Well, a trajectory is a solution x tilde with a corresponding input u of tilde t, such that d by dt of x tilde of t is equal to f of x tilde of t, u tilde of t. So we have some nominal trajectories and inputs, x tilde and u tilde, that satisfy our differential equation. And now we want to take a small perturbation around that trajectory and see if we can describe the system. And so, sort of no big surprises here. We're just going to replace everything that was x star and u star before, corresponding to our point, with our trajectories instead. So if we want to linearize around a trajectory rather than a point, step one is the same. We introduce variables corresponding to the deviations around the trajectories. So delta x is equal to x minus x tilde of t. So delta x now measures the distance to your trajectory. And we do the same for u, so delta u is u minus u tilde of t. And then step two is also the same. We try and rewrite our differential equation in terms of these new variables, and we're looking for something on the form d by dt of delta x, so the rate of change of our deviations around the trajectory is equal to some matrix A times delta x plus B times delta u. So exactly the same, linear dependence on the state deviations and linear dependence on the input deviations, plus some higher order terms that depend on delta x and delta u. The only catch now is that all these things start to become time dependent. So A is in general going to be a function of time, so is B, and so is this term with all the extra stuff in it. So this is what our linearization around the trajectory will look like. How do we find these matrices A and B? Well, we do it in exactly the same way as before, and it's definitely much easier to use the Jacobian representations this time. So to find A of t, the first thing we do is we compute our big Jacobian matrix. So here we have df1, dx1, df1, dx2, and we fill that out, and df2, dx2, and so on. The only difference is, rather than evaluating this Jacobian at the point x is equal to x star, we now evaluate it at x is equal to our equilibrium trajectory. And now you start to see this is where the time dependence comes in. So if any of these terms depend on something that's time varying in the trajectory, you'll get a corresponding time varying term in this linearization. And B of t can be found in the same way. I should have also added in this dependence. And here we have df1, du1, df1, du2, and so on, and also evaluated at our equilibrium trajectory. So let's put those times in there. And maybe the easiest way to try to make sense of this is to just see it in an example. So let's consider this sort of simple rocket setup here. So what's going on? Well, we have a rocket which has mass, m of t, and the rocket is a height q from the ground, and we apply a force, u, to our rocket with our thrusters, and we also have a gravitational force acting on our rocket. But the catch is that the mass of our rocket is changing. As we burn fuel, the rocket gets lighter. And so, in particular, we're going to say that m dot is equal to minus u. So this is a differential equation capturing this model of the mass going down as we burn more fuel. And now let's try to linearize this model around a trajectory corresponding to u is equal to u star. So we start to apply a constant input to our rocket, and we'll get some nominal solution, and that's going to be our trajectory. So this is a constant. This doesn't look too interesting yet. But now we see when we solve this differential equation, we find that m of t is equal to minus ut plus some constant, which in this case will correspond to our initial mass. So this is our trajectory for the mass, and we can similarly find our trajectory for q and q dot. We're not going to do it because it's going to turn out that we don't actually need these terms, but you could just solve to find some nominal trajectory which would be linearizing around. In fact, it's sufficient to know that we can do that in order to be able to do the computations in this case. So in order to use all of this machinery over here, we have to put this into our standard state space form. And so doing that quickly, we do it in the usual way. And as always, when we have these differential equations that depend on higher order derivatives, we need to add q dot and q to our state vector. And this time we also have the mass m in our state vector. And this has to be equal to some function of the system state and inputs. Well, if we divide by m of t here, we see that we get u over m of t minus g. d by dt of q is just equal to q dot, and this thing here is minus u. And this is just a function of our state and input, and this is the derivative of our state. So this is in our standard form. We're now ready to just fall on all the machinery over here and linearize around this trajectory. So let's do it. So delta x is equal to our state x minus our equilibrium trajectory. And what is that? Well, it's these nominal solutions. I should put q tilde, using tildes here. So we've got some trajectories for q tilde of t and q tilde dot of t. We could have solved for them by solving this differential equation with this particular input, but we're not going to need them, so we didn't bother. And here we have the initial value of the mass minus u star t. So this is our trajectory for the mass. We burn constant fuel. We're just losing mass at a linear rate. We have some nominal trajectory that the rocket is on. This is what we're going to linearize around. This is our equation. So let's do it. And now we know that d by dt of delta x is equal to some A matrix, and that's going to be given by df d1 dx1, df1 dx2 dx2, and so on. So let's just fill this out. and that's all going to be multiplied by delta x. So let's take the first row. We need to find df1 dx1. So x1 is q dot. This term doesn't depend on q dot, so we've got a 0 in here. Now we want df1 dx2. So what depends on q here? Well, nothing here depends on q, so we get another 0. Finally, we need df1 dx3, and so we need to differentiate this with respect to the mass. So we've got u over m, and so when we differentiate that, we get minus u over m squared. So this is just the derivative of this term with respect to m. That's the top row. F2, this one's always easy. It's just 1, 0, 0. So this is saying, so we need to find df2 by dq dot, but it's just equal to q dot, so dq dot by dq dot is just 1, and it doesn't depend on anything else, so we get zeros there. And then our final equation, well, we see that m dot just depends on u, so it doesn't depend on the state at all. So we have zeros here. And then we have to evaluate this at the equilibrium point. So the equilibrium point, we substitute in our values, and u at our equilibrium is u star. And this m squared, this we just substitute in our expression for the mass. So this whole term here, it becomes u star over m init minus u star t squared. And this is the term that goes in here, and so this is our matrix A of t. And we can do the same thing for B of t. And there we have it. We have our linearization around a trajectory. Things are now time varying, which means we can't use our little tricks based on looking at the eigenvalues of the A matrix anymore, but at least the concept of linearization passes through, and maybe we can come up with some more tools to analyze this.